today we're going to be exploring generative networks for image generation. The motivation is that generative models have shown their power in many different applications. Also, diffusion models are claimed to yield better results than GANs. So in this project, we really want to explore and compare different GANs and diffusion models on image generation tasks to learn about their insights, their disadvantages and advantages. The scope of the project is to train 4 different GANs and a diffusion model on 3 different datasets, the Flower, Classroom, and Pokemon Dataset, and then evaluate the generated images on FID scores and inception scores.
Deep convolutional GANs are extension from vanilla GAN but replaces dense layers with convolutional layers, while DC GAN uses binary cross entropy loss in its discriminator. LSGAN uses mean squared error loss. WGAN GP is an improvement over Jensen-Shannon divergence used in DC GAN and has Wasserstein distance instead. Also in WGAN GP, discriminators trained more than the generator, hours was 5 iterations. Results for the Pokemon dataset. Mold collapse was a major problem of DC GANs, where the generator finds a good subset of images that can fool the discriminator really well, but this subset is not always realistic or causes the generator to produce the same type of images. In the Pokemon dataset, purple and blue creatures are repeated frequently, and all the generated images have similar shapes. Another problem of DC GAN was instability. When I changed the model parameters slightly, the gradients quickly vanished. LSGAN was more stable because MSE loss introduces regularization. However, LSGAN started to generate accurate representations at later stages compared to DC GAN. Mole collapse still exists, specifically for Pokemon, but generated images are a little more varied compared to DC GAN. The WGAN GP has better training stability because Wasserstein loss is continuous everywhere, but differentiable almost everywhere. So there's no vanishing gradients happening. It offered better quality and a lot less mode collapse, but was slower in general.
Now moving on to the reimplementation of StyleGAN. Our model architecture closely follows the NVIDIA paper, but we reimplemented it in PyTorch. The model has 3 main components. One is the mapping network on the left. It consists of linear layer to produce a latent vector in an intermediate latent space where each element represents a disentangled feature. On the right is the image synthesis network, which consists of eta-in and convolution layers. We also have a discriminator. StyleGAN produces high-resolution images. It was improvement upon progressive GAN. We're using Atom Optimizer and R1 regularization loss function. We trained our reimplemented StyleGAN on 2 datasets, the Pokemon and Flower dataset. We tried various different parameters for training, and here are the settings that produce pretty good results without taking too long to train, about 8 GPUs for 20 hours. Here are the generated images after training. On the left are images for training on the Flower dataset. The flowers are pretty realistic. Right are images generated for training on the Pokemon dataset. The images are less realistic, but we believe it's because we do not have enough training images for Pokemon as we did for the Flowers dataset.
The diffusion model consists of a forward diffusion process that gradually adds noise to the input to generate training data and a backward denoising process that predicts the noise level when given a noised image as the input. The backward denoising process is implemented using UNet and embeds the time step information into the downsampling and upsampling blocks. The experiment settings are shown as follows. The Atom Optimizer and the L1 loss function are used for training. The diffusion model with attention blocks applied to the residual images is also used for experimentation. While the original diffusion model was able to achieve a lower loss and better IS, diffusion model with attention performed better in terms of FID. These are the generated images. There are some random color pixels in the generated images, which is especially obvious when trained on the Pokemon dataset where the backgrounds are mostly white. Also, diffusion model with attention does not seem to generate better results than without attention, but this might be due to the fact that the model is bigger and would require more epochs in order to generate a better performance. Diffusion models generate images of better quality, are easier to train, and do not suffer from the mode collapse problem. However, they take longer inference times and may generate some random color pixels. In conclusion, WGAN GP performed the best in terms of FID, and diffusion model performed best on the Oxford Flower dataset in terms of IS. In the future, we plan to fully utilize the style mixing feature in StyleGAN, train the diffusion model with attention for more epochs, and look into the problem of random color pixels. These are the references, and thank you all for listening.